This is the redox chart. On the left here are the oxidizers. On the right are the reducers. The oxidizers take electrons, so fluorine takes electrons. Ozone and acid takes electrons. Did we already go down the whole list? Where did we stop? All right, the way this is, it's ranked. And so at the top of the chart is the strongest, most powerful oxidizer. Fluorine really wants to take 2 electrons to form 2 fluorides. So fluorine is the most powerful. The second most powerful oxidizer on this chart is O3. O3 is called ozone. It's ozone and acid. H plus is acid, so I'll just say ozone and acid, or ozone plus. And then this one, we didn't learn how to name this one. It's not one of those ones we learned. So S2O8 minus. This one you should know the name for, H2O2. Hydrogen peroxide. This one? Permanganate and acid. So both of these are an acid. Hydrogen peroxide, permanganate. This is lead 4 oxide is correct. Lead 4 oxide and acid. This is no, this is chloride over here. This is called chlorine. Like fluorine. Chlorine. This is called dichromate in acid. No. Permanganate's MnO4 minus. This is not. What's that? That's a compound, not an ion. No. No. What's the charge on manganese? What's the charge on oxide? 2 minus. We have 2 of them. So minus 2 gives us a total of -4. This must be plus 4. Add up to 0. So it's manganese 4 oxide in acid. This is oxygen in acid. This is iodate in acid. Bromine. Nitrate in acid. Nitrate in acid is called nitric acid. Or it doesn't have to be nitric acid. What you could have is you could have like sodium nitrate salt and hydrochloric acid. That would make this combination. So it doesn't have. It could be nitric acid, or it could be two sources. One source for nitrate, like sodium nitrate. One source for H plus, like HCl. So that's why it's written like this. All these are powerful oxidizers here, strong oxidizers. Now we're getting to more moderate oxidizers, like this. Silver ion. We have to distinguish between silver metal and silver ion. Does silver jewelry stain your skin black? No, but silver ion does. So silver jewelry is okay. That's the difference. Krakalici calls this Dr. Jekyll and Mr. Hyde. Okay, what's this? Iron 3 ion. This one? Oxygen and. Didn't we just see oxygen and acid? Am I going in circles? Didn't we just see oxygen and acid? The other one has 4 H pluses. This one has 2 H pluses, so it's different. More acid here. And then what else is different? Yeah, this one forms water. This one forms hydrogen peroxide. Which one is a more stable, more favorable product? Water or hydrogen peroxide? Water, turns out, is more stable. And so this one is going to be stronger. If you have enough H plus, then we want to go to water. If we don't have enough H plus, we might go to hydrogen peroxide or something like that. Probably not, but we go with the stronger one, this one. So we ignore this one. Go with that one. What's this? iodine, copper 2 ion, sulfate, and acid. Again, this could be sulfuric acid, or it could be like sodium sulfate with hydrochloric acid. Sodium sulfate would provide the sulfate, hydrochloric acid would provide the H+. Then we can have this combination here. Then this is stannic ion, or tin 4, this one. Sulfur in acid. This one is just acid. Acid alone would be it. And then lead 2, tin 2. So you know tin 4 is a better oxidizer than tin 2. Well, what do oxidizers want? Oxidizers want to take electrons. So which one would take electrons? More favorably, or which ones would take electrons more energetically, or which ones have a stronger attraction for electrons? Tin 4 or tin 2? Tin 4. Why would tin 4 have a stronger attraction for electrons? Higher charge, higher positive charge. Electrons are negatively charged. So. Tin 2, then iron 2. Iron 2, no, iron 2 is a much weaker oxidizer than iron 3. And then zinc 2. You know, when we start getting to iron 2, tin 2, these are very weak. Lead 2, you know, these become weak oxidizers. They don't have much of a pull for electrons. At the bottom of this list is the worst oxidizer. So we go zinc, aluminum, and then lithium ion is the worst oxidizer. The strongest oxidizer is fluorine at the top. The worst oxidizer is lithium. All these are weak. That's the oxidizers. On the right-hand side, we have the reducers. The reducers give up electrons. Does lithium ion have a very strong pull for electrons? No. It's a weak oxidizer. Lithium doesn't have a strong pull. That means if lithium gets that electron, it doesn't hang on to it tightly. And so we don't have two separate charts. We have one chart for both the oxidizer and the reducer. It's the same thing. We have one chart for the acid and the base. And so there's something called conjugate relationship. So if lithium ion is very weak, then its conjugate, lithium metal, the reducer, is very strong. So this is a powerful reducer. Lithium easily loses that electron to form lithium ion. And so lithium metal here, lithium solid, is the most powerful reducer on the chart. It's the species that loses electron most easily if we go reverse here. You know, we can read this chart either way, forward or reverse. If we have lithium metal as a reactant, it'd go forward and it'd form lithium ions. So we always end up flipping these around, depending on what we have on the reactant side. So lithium is the best. The next best reducer is okay, what pattern do you see here for the strongest reducers? Group 1 and Group 2. Group 1 being better. And so it's the far left of the periodic table. At the far left, they want to give up the electron more easily. Then aluminum is kind of in the middle. Zinc is in the middle. It's in transition. And then iron, tin, lead. And then hydrogen can give up electrons as well. When hydrogen gives up electrons, we get 2 electrons in the H+, so we lose electrons. What's this? Hydrogen sulfide. This would be hydrogen sulfide gas. If this were aqueous, what would I call it? If this were aqueous, I would call it hydrosulfuric acid. Well, that's going to form sulfur going this way, lose electrons. Hydrogen sulfide, hydrogen's +1, sulfide is -2. So it's -2 going to 0. So it's got to lose 2 electrons. What's this? Tin 2 can go to tin 4 by losing 2 electrons. So this is what happens to tin. Tin's a 2-step. tin first goes from tin 0 to tin 2, in the process of losing 2 electrons. And then subsequently, the tin 2 can go to tin 4 by losing another 2 electrons. This would be, SO2 is called sulfur dioxide. Sulfur dioxide and water. What's the charge on sulfur in sulfur dioxide? If oxide is -2, we got 2 of them, then sulfur must be +4. So here we're going from sulfur +4, and what's this called over here? Sulfate. What's the charge on sulfur and sulfate? Well, the charge on the ion is 2-, but each oxide is -2, so -2 times 4 is -8. -8 plus what gives us -2? -8 plus 6 gives us -2. So this sulfur is +6. So we go from sulfur +4 to sulfur +6. Well, if it's going from +4 to +6, it's got to be losing 2 negative charges, 2 electrons. This one is going from copper 0 to copper 2+. So going from copper 0 to copper 2+, we got to lose 2 electrons. So the reducers lose electrons here. This is what? Iodide going to iodine. Iodide and iodine are 2 different species. Just like sodium metal and sodium ion. If you're on a low sodium diet, does that mean you cut back on sodium metal, or does that mean you cut back on sodium ion? Which one? If you're on a low sodium diet, do you cut back on sodium metal or sodium ion? Sodium ion. Because if you were to eat sodium metal, did I show you that video? If you were to eat sodium metal, your mouth would catch on fire. I'll just show that video there.
30,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The element cypress chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
So yeah, you don't want to eat sodium metal. Sodium ion's okay, because a powerful reducer like sodium is going to make a weak oxidizer of sodium ion. So this is the Dr. Jekyll, Mr. Hyde. Sodium is very violent. Sodium ion is very mellow, very stable. Same goes, you know, for these. ion versus copper metal, or silver. We're going to get into it there. This is iodide. This is, hydrogen peroxide can go both ways. If something like an acid goes both ways, we call it amphoteric, but we don't have a similar term for redox. In redox, hydrogen peroxide could either be an oxidizer, in the top 5 of oxidizers, or it can be a reducer. It's not a great reducer, mid-level reducer. So it could go either way. If hydrogen peroxide oxidizes something, it takes electrons. We end up with oxygen of -2. But if something takes the electron away from oxygen here, then we end up with 0. It could either gain or it could lose electrons. In this case, it's losing electrons. Going from oxygen, hydrogen peroxide is unusual. Oxygen to -1, over here to oxygen to the 0. We got 2 of those, so we can lose 2 electrons. How about this one? That is iron 2 going to iron 3. Process losing electrons. And so what happens with iron metal? Iron metal goes to iron 2 goes to iron 3. This is silver. Silver versus silver ion. Silver metal is stable. Silver ion is a moderate oxidizer. Silver is not that great of a reducer. This is called nitride ion is NO2 minus with a charge. This is a neutral diatomic binary molecular compound. Yeah, nitrogen monoxide. Nitrogen monoxide or nitric oxide is the name of this. What's the charge on nitrogen? That's its normal charge. Nitrogen's charge can vary. Nitrogen's charge or oxidation state can vary. When we look at the periodic table, it can vary. So for example, fluorine's -1, fluoride, oxygen's -2, oxide, nitrogen is -3, nitride, -3. But if we approach it from the other side, group 1 is +1, group 2 is, group 3 is plus, group 4 is plus, group 5 is +5. So the charge on nitrogen varies from -3 to +5. You can have a charge between those, or the limit. So if we pretend that oxygen is -2, then that means nitrogen is, well, if oxygen's -2, then nitrogen's going to be +2. And then what's this called over here? Nitrate. And what's the charge on nitrogen and nitrate, the oxidation state? The net charge is -1. So we got 3 oxides, -2, -2, -2 is -6. -6 plus what gives us -1? -6 plus 5. So we're going from +2 to +5. In order to go from +2 to +5, we've got to lose how many electrons? 3 electrons. And then we have bromide going to bromine. And then what's this? Iodine. I saw iodine before. Normally when we think about iodine, iodine's an oxidizer like chlorine, chlorine, bromine, iodine. But over here, iodine's acting as a reducer in the presence of water. And that's going to form, what's this? Iodate. And so iodine's going from 0, there's no charge there, to what's the charge on iodine in iodate? Well, this is -1, but it's plus 5. Then we have water going to oxygen. Water can be a reducing agent. Manganese 2 going to manganese 4. Chromium 3 going to dichromate. Good. What's the charge on chromium and dichromate? 6. Chromium 3 going to chromium 6. Chloride going from -1 to 0. lead 2, going from lead 2 to lead, this is lead 4 oxide. Manganese 2 going to manganese, well this is, what's this anion called? Permanganate. What's the charge on manganese and permanganate? +7. So we're going from manganese 2 to manganese 7. In the process, we got to lose 5 electrons. This is water going to hydrogen peroxide. This is sulfate going to this usual. What's the charge on sulfate?
2-.
Yeah. And what's the charge on oxygen in sulfate? The net charge is 2-. And so each oxygen is -2. We got 4 of them, so that gives us -8. -8 plus what gives us -2? -8 plus 6 gives us -2. All right, take a look at this. What's the charge on sulfur here? +7. +7 is correct. Now, +7 is unusual. Can somebody tell me why sulfur +7 is unusual? Yeah, because we expect the maximum positive charge on sulfur not to be +7. We expect it to be +6. So it's unusual. It's an unusual charge to have on sulfur, which doesn't make it very happy. And so if you look at it, it's the 3rd most powerful oxidizer on this chart. It really wants electrons. You say, why does it want electrons? It's got a -2 charge. A -2 charge, you know, I know Coulomb's law. Coulomb's law is like charges attract or like charges repel. Like charges repel, so why is this attracting electrons? This is a negatively charged species. Not only is it negatively charged, it's -2, attracting electrons. Well, it's not the whole ion that's attracting electrons. This -2 comes from an imbalance of the oxide, so that -2 belongs to the oxide. What's attracting the electron is the sulfur in this. The sulfur is +7, which is not happy at +7, be unstable. And so this is why, so this is kind of an exotic species. This is why you haven't learned how to name this, because it's not common. It's pretty unstable. So kind of ignore it. Same thing with ozone. Ozone's not that common, it's pretty unstable. Ozone's formed in like lightning strikes or electrical shorts. It doesn't last for very long and it causes burning sensation. If you get ozone in your eyes. Ozone's also in air pollution. Photochemical smog causes burning, irritation. Fluorine, think about chlorine. You know, if you've been to a swimming pool where they put too much chlorine in the pool, you know how irritating that is? Well, fluorine's like many orders of magnitude worse than the chlorine. If they put fluorine in the swimming pool, you'd be in trouble. Because fluorine's extremely powerful, much more powerful than chlorine. So fluoride. And so what we do is, when you look at this chart as a whole, you go, wow. I had a student, no, actually I've had multiple students ask me, do we need to memorize this? And then I said, no, you don't have to memorize it. But then they say, oh good, you know, because then they can completely ignore it. But you don't want to completely ignore it. I mean, even though we don't memorize it, you should memorize certain things. You know, do you see any patterns in this? This is what scientists do. I mean, if you want to know what scientists do, they take a lot of observations. This is a lot of observations, and what do they do with all these observations? They look for patterns. And so if you can recognize some patterns, then, you know, this is not a comprehensive list. If you're given, or you're thrown something that's not on this chart, you could probably figure it out, you know, where it kind of belongs. So, you know, if you're a metal, what do you think about metals? Where do they belong? Metals are typically the reducer end, except for some, you know, like silver. Like, for example, gold's not here. But where would you position gold? Not the exact precise position, but just relatively, where would you position it? Well, a reducer and oxidizer. Lithium's very easy to oxidize. You know, when we're talking about oxide, like iron's easy to oxidize. Why? It rusts so easily, right? Aluminum's even easier, but when you look at aluminum isn't rusting like iron does. This is aluminum here. The reason aluminum doesn't is aluminum does oxidize very easily, except when it forms the oxide, it forms a protective coating. And so there's a protective coating of aluminum oxide on the surface here. Whereas for iron, that protective coating is very porous. When we look at rust, it's the coating is a lot more flaky, it's a lot more porous, so it tends to corrode through, whereas aluminum forms a nice thin barrier there. So a lot of these, you know, metals corrode pretty easily here. Does gold rust easily or corrode easily? No, so gold would be way up here somewhere. Does gold corrode easier or more difficult than silver? In other words, is it easier to oxidize gold or harder to oxidize gold? Harder, so it's less than silver. Somewhere up there. And so there's certain patterns here. So the strong reducers, typically metals, followed by some others. Species. We look at the oxidizers. The strong oxidizers have something in common? The strong reducers are on the left side of the periodic table. The strong oxidizers on the right side of the periodic table. And so at the far right, except for the noble gases are. So we got fluorine, chlorine, bromine, oxygen, sulfur. Those species. And then we see, you know, the charged ions. The charged ions, iron 3 versus iron 2. Which one's better? Iron 3. So the higher the charge. And then we see other species. What do these species have in common? These anions, nitrate, iodine, permanganate, dichromate. What do all those anions have in common? They all want electrons, but they're all negatively charged. What they have in common is oxygen, but there's something else they have in common. It's not the oxygens that make them a powerful oxidizer. What makes them a powerful oxidizer? It's the positive charge on the other atom. And so when you start looking for patterns, you know, then you're better. You're better than just memorizing this. Well, actually, memorizing this is not bad. I mean, if you can memorize this, that's great. But if you recognize the patterns, then what you can do is you can predict things. You know, it depends on how you memorize this. If you memorize it just as straight memorization, then it's worthless. You know, in certain respects, because you can't predict anything. So you want to be able to predict things that aren't on the chart. You know, that. Try to do things that way. So we have oxidizers and reducers. So I'm gonna, did I do combustion already?
We started. Yeah.
Okay, so we finished combustion. So we're on single replacement right now, right? So let's go on with single replacement. The nice thing about single replacement is what? It's a simple pattern. The bad thing about single replacement is a lot of exceptions. The pattern is too simple. That's the problem. But let's ignore the exceptions for now, and then we're just going to look at the pattern. A plus bx yields ax plus b. Now the driving force is we're going to compare A to B. What the driving force is we want to go from more active to less active. Now, let's take a look at the activity series here. So at the top of the activity series is lithium. Lithium is the most active. And then does that sound familiar? Yeah, that sounds familiar. In fact, what we're looking at, what does it mean to be active? Well, in the context of single replacement, it means this. We're looking at the strength of the reducing agent. And so lithium is the most powerful reducer. It's the most active reducer. It's the most active, followed by potassium, calcium, sodium, magnesium, etc. And so what we're essentially doing is this. Active, in this sense, just means reducer. I should say, more active reducer. And so what we do here is we say when we're going from more active to less active, we're going from a stronger reducing agent or stronger reducer to a weaker reducer. Lithium is the most powerful reducer. Oh, I forgot to bring my book. But let's try some examples from lab. Zinc and hydrochloric acid. No, it's copper 2 sulfate. Zinc and copper 2 sulfate. So what's the formula for zinc? Zn. What's the charge on zinc? Plus is not correct. +3 is not correct. Plus is not correct. 0 is correct. We have two. It's either 2 plus, which would be called zinc ion, or it's 0, which would be zinc metal or zinc solid. And so this is not specified. This doesn't say zinc ion. And so we're just going to assume it's Zn. And the state's going to be solid. So this is just zinc metal, not zinc ion. Plus copper 2 sulfate. What's the formula for copper 2 sulfate? SO4. Okay, this is copper sulfate solution. Normally copper sulfate is a solid. Is it a soluble solid or an insoluble solid? So we need to know the solubility rules, and the solubility rules go like this. Sulfates are soluble. Sulfates are soluble except for which ones? Like I go in this pattern: silver, lead, mercury. Well, I go mercury, 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 mercury 1, mercury 2. Mercury, mercury, calcium. Calcium is always 2. Strontium and barium. So this is not one of the exceptions, so this is soluble. All right, and so this fits the pattern. It's an A plus BX. This is not metathesis. Why is this not metathesis? It's not double replacement, but does it have to be double replacement? So what if I did this? What if I went like copper 2 plus Li3PO4? What's Li3PO4 called? Lithium phosphate. Is this metathesis? Or is this single replacement? This fits the A plus BX pattern, but this is not single replacement. This is metathesis. What's going to form? What's going to form is copper phosphate. What's the difference between this one and that one? Well, this is why we're probably going to have to put some more verbal. A cannot be an ion. A has to be an element. And so the pattern here is element plus a compound. Element plus a compound yields a compound plus an element. This is not copper the element. Copper the element would be Cu solid with a 0 charge. This is copper metal. This is copper ion. So the copper ion can come from any source. Why? This reaction is metathesis. This is why I don't call, metathesis, I don't call double replacement. I call metathesis what? I call metathesis favorable ion combination. So you're looking for favorable ion pairs. One way to figure out what a favorable ion pair is by doing double replacement. So for example, we'll take the cation A and the anion D. Is that a favorable pair? And then we'll take the cation C with the anion B. Is that a favorable ion pair? So what we're doing in double replacement is we're trying two new ion pairs and seeing if one of those is favorable, or maybe both of them are favorable. But it doesn't have to be in this pattern. This is what screws up people, because if it's not in the AB plus CD pattern, then they're lost. They can't do anything because it doesn't fit the pattern that they memorized. But, we don't have to have that pattern. So, for example, if I have silver ions and chloride ions, do these two ions like each other? Yes, they do. Well, I'm going to form silver chloride. This is metathesis. And so AB plus CD is just one way to help you figure out the ion pairs, but you don't need this pattern. We just mix and match the cations with the anions to see which ones like each other. That's all we do. And so if I've done this in the past. I've given this AB plus CD plus EF, and lots of people leave this blank. They're totally lost because it's AB plus CD plus EF. They don't know what to do because they only recognize certain patterns. But it's simple. You try all combinations of cations and anions, and then you see, are there any favorable ones there? And so this is why I call them metathesis. I don't call them double replacement, because double replacement is only one type of pattern to help you figure out mixing and matching cations and anions. But all we're doing is trying different combinations of cations and anions and seeing which ones work out. So metathesis is ion combinations. Well, this is an ion. This is not an ion, so this is critical here. For single replacement, for this is not metathesis here, because if this were an ion, then yes, the metathesis, we can try mixing and matching ions. But since this is the element, then there are no ion. The only ion pair is copper and sulfate, but we already have copper 2 and sulfate ions. And so we don't have anything new. And so this is critical that A is the element here. A is the element, not the ion. And so there's no charge on that. If there's a charge on that, then we're talking about a different type of reaction. Metathesis.
Favorable ion combination just
It'll precipitate is one possibility. Another possibility is
strong acid.
not strong, stronger. Stronger acid to weaker acid. And the third possibility is gas. Those are favorable ion combinations. And so we recognize this as being the single replacement pattern. What are the products? So A plus BX yields AX. Okay, now it's going to be zinc sulfate. Zinc sulfate, what's the charge on zinc? 2, and sulfate is 2, and so it's just a 1-to-1 ratio. 2 plus and 2 minus. And then we're going to form copper. What's the charge on copper here? I know the charge on copper here. The charge on copper here is plus 2. The charge on copper here is 0. This is copper metal, not copper ion. It's copper 0. And so this completes our pattern. A plus BX yields AX plus B. Now, we don't know if a reaction is going to occur. What we have to do is we have to determine if there's a driving force present. And so we're going to compare the activities of zinc and copper. So I could use, in this activity chart, lithium's at the bottom. And so it gets weaker as we go up. So here's zinc. And here's copper. So which one's more active, zinc or copper? Zinc. This is why, you know what pennies are made out of?
95% zinc, 5% copper.
Yeah. They have a zinc core, and the zinc core is covered with a copper protective layer. And if they made it out of pure zinc, it's not going to last very long because zinc is a pretty active metal. It's really susceptible to corrosion. And so the zinc is more active. And the copper is less active. So what people do is they make, have you ever made a hollow penny? Some people make hollow pennies. What they do is they scratch off a little bit of the copper and they get some acid. The acid will eat away the zinc on the inside, but leave the copper on the outside, so you get a hollow penny. I'll make a hollow penny. They're pretty easy to make. All right, so we have driving force here. We're going from more active to less active. That's our driving force. In other words, we're going from a stronger reducing agent, zinc, to a weaker reducing agent, copper. Copper doesn't give up its electrons so easily, like zinc does. And so this would be the CE and the driving force. And then we go on to the IE. For the IE, we just ionize the strong electrolytes. Strong electrolytes with strong acids, strong bases, and the soluble salts. So is zinc a strong acid? No. Is it a strong base? No, it's not a strong base. Is it a soluble salt? No, it's an element. It's not even a salt. So it's zinc. We leave it alone. Copper 2 sulfate. Strong acid? No. Strong base? No. Soluble salt? Yes. So the soluble salt, we're going to split it up. We're going to split it up into what? Cu 2 plus SO4 2 minus. zinc sulfate, strong acid? No. Strong base? No. Soluble salt? Yes. Sulfates are all soluble. Unless you're dealing with silver. No. Lead? No. Mercury? No. Mercury? No. Calcium? No. Strontium? No. Barium? No. So this is not one of the exceptions, so it's soluble. So it's going to be Zn2 plus sulfate. And then copper metal. Strong acid? No. Strong base? No. Soluble salt? No. So just leave it alone. Copper metal. Yeah. Now we look for spectators, things that didn't change. Did the zinc change? We went from zinc to zinc. But there was a big change. And the big change is in the charge. We went from zinc 0 to zinc 2 plus. That charge makes a huge difference in chemical properties. And so zinc reacted. How about copper 2? Yeah, copper 2 reacted. How about sulfate? Sulfate didn't react, so that's our spectator. So we're going to get rid of the sulfate in our NIE. So it's going to go zinc solid plus copper 2 goes to zinc 2 plus copper 2 plus. Now take a look at what happened. What happened to zinc? Did zinc lose electrons or did zinc gain electrons? Zinc lost electrons. If something loses electrons, are they the oxidizer or are they the reducer? Reducer. So zinc is the reducer. What happened to copper? Copper went from 2 plus to plus. Is that right? No, I made a mistake. Where's my mistake? Yeah, it's copper solid. So we went from copper 2 plus to copper 0. So we must have gained electrons. So what gains electrons is the oxidizer. The oxidizer takes electrons. The reducer gives up electrons. So basically, copper 2 took electrons from zinc, and these are the products that form here. The oxidizers take electrons. If you look at everything on the left here, everything on the left is an oxidizer. What are they doing? They're taking electrons. Plus 2 electrons, plus 2 electrons, plus 2 electrons, plus electrons. So let's analyze the single replacement pattern a little deeper and see what's happening. These are redox reactions. There's an oxidizer and there was a reducer. And so these are the assigned roles. Assigned roles. A is the reducer plus B. X. B is the oxidizer. X is the spectator. And then we're going to form AX plus B. Now, when we do these reactions, we compare things. So, for example, here, we always think of a competition between the forward reaction versus the reverse reaction. Which side is more favored? In other words, which side is more stable? Which side is less stable, higher in energy? So in this case, which one is a more stable metal? Zinc or copper? Which one is the more stable metal? Copper is more stable, so it's tilted like this. Copper is more stable, zinc's less stable, so it's downhill going this direction, right to left. That means we have a driving force. And so copper is more stable, and so what we say is it's less active. This is more active, so it's like this. We're going from more active, less stable, to less active, more stable. We do this as a competition, so the way we do this in proper redox is we would say zinc. Zinc would be a stronger reducing agent. This is RA stands for reducing agent. S just stands for stronger reducing agent. And then we compare it. if we go backwards here, who's losing, who's gaining? So Zn2 plus going backwards. We go from Zn2 plus to zinc. So did that gain or did that lose? It gained. And so the species that gain, are they called the oxidizer or are they called the reducer? They're the oxidizer. Oxidizers gain or take electrons. And then copper loses, so that's the reducer. So if we were to analyze this a little deeper, then we're going from a stronger reducing agent to a weaker reducing agent. So that's a driving force. We want to go from a stronger reducing agent to a weaker. In other words, a more active reducing agent to a less active reducing agent. But that's activity for reducing agents. We also have activity for the activity for the reducing agents is set by lithium being the most active. But we also have activity for the oxidizing agent. For oxidizing agent, what's the most active oxidizing agent? Fluorine is the most active. And so we're going from, let's take a look at the oxidizing agent. We're going from copper 2, which is at the top there, and zinc 2, which is here. Which one is a more active oxidizer? Copper 2. And so in other words, we're going from a stronger oxidizing agent, which we'll call OA. OA is going to be for oxidizing agent. And so this is more active oxidizer to a less active oxidizer. Copper 2 is a more powerful oxidizer than zinc 2, so this is going to weaker oxidizer. So we're going from stronger reducing agent, stronger oxidizing agent, to weaker oxidizing agent, weaker reducing agent. This is a driving force. We only need one of these because of the seesaw relationship here. It's called the conjugate relationship. If one of these is true, the other must be. And so it's always going to be strong, strong to weak, weak, or weak, weak to strong, strong. It's never going to be strong, weak, strong, weak. That would never happen. And so this is why we only look at the activity of the reducing agent, and we don't consider the activity of the oxidizing agent because we don't have to, if we get it right. But we might as well look at it. Now, when we set it up in the pattern like this, A plus BX pattern, we're setting up the roles. Everybody has a role. A is what? Reducer. B, all right, and X is the spectator on the left. On the right, A is going to be the oxidizer, B is the reducer, and X is the spectator on the right. And so everybody has an assigned role. The exceptions come because they don't play their assigned roles. We'll talk about that later. So for right now, let's just get some practice doing single replacement using just the standard method. And so the next reaction is going to be copper and zinc sulfate. Okay, why don't you, well actually it's a break time, so we'll take a break and then we'll come back and do this one.